We'll just move right on to the presentation. Loren, KEØHZ, is going to give us a nice presentation on HamSci. So, Loren, we'll turn it over to you.
All right.
And if we can, Stephen, allow him to screen share. Thanks.
Also, while we're getting ready, I've also started the recording so we can put it up on YouTube.
All right, so I think navigation here. I'm going to stop sharing for a second and get my presentation up here ready. Try this again. And it disappeared on me. I see a picture of all you guys. And
it's working. We see it.
Oh, you do?
We do. You need to go to presentation mode, though.
I'm trying to find that because you guys are blocking it all here. All right. Presentation mode, and
better. You still have the.
We swap this.
There you go.
All right. So the discussion is about HamSci, the Ham Radio Science Citizen Investigation. How ham radio operators, or in this particular case, the citizen scientists, are supporting the some radio scientific endeavors. So we're going to do an experiment. Stephen, can you bring up that first question? Is everybody seeing that on your screen? Are you currently participating in HamSci? Yes or no? And just out of curiosity, we're going to get a look at some numbers. And this is not a scientific poll by any means, but I think there'll be some interesting results. Do we have some totals, Stephen?
We're sitting at 27 people answered so far of 40.
Good. Let's see what the numbers are.
We're now at 30 of 40. Holding at 75. 32.
So what are the results?
Are you ready for me to end it?
Sure.
All right, here we go. Can everybody see that? Nope, here it comes.
Yes, 3%. 97. So out of about 40 people, 3%, we got about 1 and a fraction are currently doing that. So let's see. So this may apply a little bit to primarily the HF operators, but how many of you guys are using Whisper, WhisperNet, PSK Reporter, Reverse Beacon Network, DX Cluster, CW Skimmer, and we'll get into this a little bit more. But if you're using any of these, click on them, and let's just see about some numbers. And the reason for doing this will make itself clear here in a moment. If you don't know what they are, don't worry about it. We'll explain a little bit here going forward. Stephen, let's see what our results are.
We're sitting at about 42%. 17 people of 40 have indicated anything. You ready?
Yep. So there is some usage. Interesting. Well, you're already contributing to HamSci if you're using any of these. So here is a WhisperNet view. I pulled this one for the 20-meter band about a week ago, 5/11 at 02:01 UTC, so about 8 p.m. in the evening. And this was a list or showing contacts or signals that were being heard on the 20-meter band over just the previous 10-minute period. So interestingly, we're getting into dusk. 20 meters is still pretty open. I don't show it into Asia, but you see a couple of lines there from the US that are being heard in New Zealand. There's still some activity at nighttime over in Europe, primarily local, probably ground wave type connections. PSK reporter, I'm not 100% certain about this, but I think FT8, well, I guess it says so. FT8 contacts, if you're using some of the digital modes, they're showing up in PSK reporter of where contacts are actually getting made. The reverse beacon network, similar kind of thing. People can post contacts that are being heard, and we're getting an idea of who can hear whom around the world. And then DX Watch is another one. But the point is, out of all of this, is that we're looking at data. I fully admit I'm a data nerd, but how can we use this information? And kind of in billing, what this topic was about, something near and dear to every ham's heart is propagation. How is my signal getting out? Who can I hear? Who can I contact? When can I contact them? When can't I contact them? So out of these observation networks, we've got data going back to 2008, which an entire solar cycle, and available in real time. So it's, there's a lot of opportunity here to figure out what's going on. So as we go forward here, first of all, I don't want anybody to get intimidated by any of this, because I'm not an expert on propagation. I am not an expert on some of the topics we're going to get into on why propagation is the way it is. But what I wanted to do, and what I'd hoped to accomplish in this, is to give some ideas on what we can use of existing tools to help us enjoy our hobby more. In the case of emergency communications, are we able to do what we need to do when we need to do it? If we're just, if we're chasing DX, what are the best times? How can we learn from that? In the course of this presentation, I've broken just about every single rule when it comes to a presentation in the number of words. So don't worry about the fact that I'm not going to read every chart that I did, but I wanted to treat this as more of kind of a white paper, and there's a lot of references. So if something intrigues you or interests you, you can go back to this at a later date and not try to understand, hopefully there's some context provided for the material here. So we're talking about citizen scientists. So I thought it was interesting. I found an explanation of what the difference is between a scientist and an engineer. And the scientists are dealing with knowledge, engineers, invention. Scientists explore laws of nature. The engineer attempts to use the laws of nature. Create theories versus implementation. Create tools, use the tools. Solve the theoretical problems or solve the practical problems. And in my mind, you don't have to be a degreed engineer, but a ham radio operator is acting as an engineer in this case. Every time we use a radio, we're utilizing the laws of nature, implementing theories, and in many cases, just getting things to work. We're solving practical problems. And that's why there is an effort here with HamSci. And the idea is to advance scientific research and understanding through amateur radio activities, exploring new opportunities, providing educational opportunities for the community and the general public. And the general public, obviously, here is the ham community, but it's even more farther reaching than that. And we'll get a couple of examples here coming up. So I'm not going to read the words. We're kind of same kind of information that we talked about just a moment ago of utilizing where is the data coming from and how can we participate. There's a couple of names here that are pretty interesting, and Greg has actually been pointing out some of the QSO Today episodes in his newsletter that he's putting out. But a key name here, and you're going to see this on a bunch of slides, is Dr. Nathaniel Frisell. He is an associate professor at the University of Scranton, but he, in essence, created the HamSci organization. They've got some really high-powered scientists that are working with them. Dr. Phil Erickson from the MIT Haystack Observatory. I think in one of the presentations I saw that he gave, one of his toys is a dish antenna. I think it might be a 40-meter antenna pointing straight up with 1.5 million watts. They're actually heating the ionosphere and taking measurements from it. So talk about fun transmitters. And then you've got the Johns Hopkins University Applied Physics Laboratory and scientists there. So there's a few projects, aside from just contributing data in the context that you're making or signals that you're hearing. There's a personal space weather station, the PSWS. There are ionospheric studies going on where there have been specific tests being taken to measure what happened for propagation during the last solar eclipse. And I've got some pictures and charts that show that. There is a satellite up where they're collecting signals and looking at propagation through the ionosphere, but they've got an activity called Golden Ears, and that is related to decoding CW signals that are provided that have been part of the data collection. And then some long names here and related to space weather that we'll talk about a little bit. And then the Aurora Saurus project, the citizen science observations of the Aurora, and not just radio signals, but just visible. Where is it visible? What kind of activity? So we'll see how some of those things relate to our activities. So a little bit about the Personal Space Weather Station. I'm guessing that a lot of you have been to the KEØHZ.com web homepage, and you see this chart displayed, the solar weather or solar data propagation. There's a bunch of interesting facts basically the current status of the sun and how it is affecting ham radio propagation. And a couple of things to point out. This number here, the SFI, is the solar flux index. Gives us an indication of how active the sun is. And when we talk solar weather, it's being driven by the sun. This is significant. Sunspot numbers, 0. This is one of the quietest suns as I've been monitoring this that I've ever seen. And here's an image of it. There are no sunspots at all, very little activity. However, there's some interesting things on here that we do want to pay attention. Daytime fair propagation on 80 and 40 meters, good at night. Fair isn't great, but it's a lot better than poor propagations on 20 meters. This was something that has popped up here just recently. 6-meter sporadic E is now starting to show up fairly active in Europe, also on 2 meters. They talk about 2-meter North American band closed. Well, I have been hearing about some 50 megahertz or 6-meter sporadic E starting to pop up in the US as well. There's been a good bit of activity here on the Front Range with people that are operating on 6 meters. So The big so what? Well, with HF communication impacts, we're talking about maximum usable frequencies. You know, at what point do we are we able to carry on a QSO above 20 meters? 15 meters, pretty quiet. 10 meters, extremely quiet, other than rare times when they've been popping up here lately, only to get better as the solar cycle starts moving from the minimum to improvement. But in many cases, just incidences that are just kind of randomly occurring, they're very hard to predict, may improve, degrade, or even block communications. And then noise. Well, something up here, the signal noise level on this chart says S0 or S1. That's pretty quiet right now. But, so with additional solar activity, you end up with better propagation, but you got noisier bands as well. So this isn't limited to just VHF communications. VHF, I mentioned the sporadic E, aurora propagation. In times of aurora, HF may be blocked, but you may be able to bounce a VHF signal off the aurora, the geomagnetic activity that's taking place and associated with the aurora, and do communications in higher frequencies. And then we've got GNSS, so a term that we typically just say GPS, but the reason GNSS is now coming into usage, general usage, is that it includes GPS and then the European Galileo, the Russian GLONASS, and the Chinese Baidu satellite constellations. We experience, because of space weather, degradation of the accuracy of our locations with the GNSS receivers. And that's due to what's called scintillations, which are perturbations within the ionosphere that the signals travel through. Again, I mentioned we're not going to become experts on solar weather here, but just this picture for reference later on of all the things that are taking place with the sun. But all of these activities affect the communications on the Earth due to the geomagnetic, the magnetosphere around us, the ionosphere, the things that happen in the ionosphere as associated by solar activity. And primarily we're talking about, on a daily basis, solar wind, but there may be flares, there may be coronal mass ejections that can cause some real significant effects. So real quick, I think some of this was probably tested at least on the general exam and certainly in the extra class exam. But the ionosphere is comprised of a number of different layers, and you see the effect, or the cartoon that indicates nighttime versus daytime. And one of the reasons that the lower bands are not that effective during the day, the 80 and 40 meter, is that the D layer predominantly absorbs the RF and doesn't allow the signals to pass through to get reflected. At nighttime, the D layer dissolves, and now we have layers in the ionosphere that will reflect signals. The F layer, when in times of higher solar activity, is better, and we can the maximum usable frequency goes up. We can see some advantages and much better propagation associated with that. I thought this was a pretty good cartoon, and here's one of the first references that it's probably, if you're interested, worth watching, because it talks about why during solar activity the location from GPS or GNSS is deteriorated. But the area over here on the left side is depicting the ionosphere. And the ionosphere is comprised of electrons which have negative charges, which these little red dots all represent. The more electrons, the more the more reflectance that will occur off of that if that signal hasn't been observed. Don't be intimidated by the chart here, but this is how that data is getting utilized in the from the PSK reporter, from the reverse beacon network, from WhisperNet. The data on this chart here is the 6th of September 2017, where there were 2 solar flares. One occurred, shown on the chart right here. This solar flare occurred just a few minutes later. And the thing about these solar flares is we know they happened only after they happened, because the X-rays that are emitted from those flares are already past us. These are really, really high energy events that strike the Earth's atmosphere and just do crazy things to the ionosphere. And here you can actually see the differences. The blue and green and yellow over here is a heat map that is representative of the number of signals that are actually being recorded. And up here it says 14% of the data on this chart was from the reverse beacon network. 86% of it was from WhisperNet. So at 20, let's look down here at 20 meters. So prior to the solar flare activity, there is a great deal of activity indicated by this heat map. This is where all of those signals are taking place. Look where the solar flare occurred and look at the number of signals. If you've ever been on an HF band and you hear about, you've experienced fading. That signal was strong. It was an S9. And all of a sudden, it's down in the noise. Well, this is a representative of that. And that flare goes by, and it takes some time to recover. Well, the larger flare here that occurs, and even more evident at 7 megahertz, is it just completely wiped out all communications right after that. So how do we know that? Well, this is where that citizen science activity is taking place. They're getting their data from our activity, and you're going to see a lot of examples here of that importance of doing that. So this same flare in the U.S. On the higher bands, there wasn't any activity. This was at night. The F layer is pretty quiet. We're starting to see a little bit of activity on 20 meters, see a little bit of a dip here. And but this is primarily now, what direction is the Earth facing when this flare went by? So the ionosphere it's like at nighttime, we're in the shadow of the sun. We're not seeing the sun. The atmosphere, the ionosphere, is not seeing it either. So you can see how the effect will vary from region to region, depending on time of day, where you are with respect to the sun. So the personal space weather system goals. Scientists want to be able to better sample the environment and understand what's going on. But hams, by utilizing a tool like this, can know the best frequencies for working DX or understanding the radio frequency interference environment, communicating better during emergencies. A little background and a couple of links on the weather station of how they work that I'm not going to go into right now. Little bit of repetition here. The objective of this system is to characterize the ionospheric and geomagnetic response to the space weather, identify the sources, understand the impacts so that we can see. But ultimately, the scientists would like hams to build personal space weather stations. I'm certain the old-timers here have heard about the organization called TAPR, the Tucson Amateur Packet Radio Organization. well, they don't do packet radio anymore, but now that group is helping to build a personal space weather station that actually can be utilized at a fairly economical price that will monitor these data sources, the reverse beacon network, WSPR, etc. In addition to it being just, a typical receiver of, we're listening to other signals, it's characterizing the noise. It has a GPS TEC stands for Total Electron Count receiver. That image we saw earlier, the more electrons in the ionosphere, the greater the impact on propagation. And then another phenomena that takes place, traveling ionosphere disturbance detectors. But it also includes a magnetometer, because that the solar wind that's taking place and the charged particles that hit the atmosphere are perturbating the magnetic field that's surrounding the Earth, which is causing aurora, which is causing a number of effects. There will not be a test on this at the end. One of the device that Tapper is building is called the Tangerine SDR, and it's a modular radio. Going back, this is the modular. It has different components that will do measurements like this. It's essentially based on a Raspberry Pi or a single board computer, and a little bit higher end SDR than we're accustomed to buying for $30 off of Amazon. But it allows beginners to have a functioning radio with a minimum number of parts, yet allow that expert user more functionality as needed, but also then to contribute something that is more geared toward the science around the radio signals as opposed to just the communication. And here's a link. There's an interview with Scotty Cowling, who is the project engineer for this particular device. And just to show you what something like this might look like, a product called the Red Pitaya. Now this is an SDR, but it's a full transceiver. HF, I think probably up to 50 megahertz, but it already has a lot of instrumentation that can be done on it. This one's not cheap. The basic unit is probably about just shy of $400 US for this, but it is available to purchase. A little bit about ionospheric studies. Again, let's, not to become experts here, but I think it's just a point of reference to the things that we hear about, and hopefully just a little bit of, a little practical understanding by just seeing what the effects are. So the SEQP, that was the called the Solar Eclipse QSO party. And there was an intentional activity to be in operation during the last solar eclipse. So the scientists were modeling the eclipse, and I can't begin, and I don't think I even want to know what a PHARLAP ray tracing device is, but it predicted that propagation would be at a minimum here. Based on the ham radio observations, you can absolutely see a dip in that. And then going back, I may have put this another slide at the end that really kind of shows the effect of what happened with the WSPR connections during that time. And you can see during the time when the sun was blocked, the ultraviolet rays that were coming through changed how the ionosphere was reacting, and significant changes in the radio propagation. Another activity that's kind of interesting, and for primarily for the guys that are doing CW, I mentioned the golden ears earlier. There is a satellite called the Casio measuring wave electric fields in the ionosphere. Well, what does that mean? It means that they're seeing signals that are taking place in the atmosphere with a rather sophisticated instrument up there. What they've done in some experiments is they tuned to the 7 megahertz 40 meter band during field day. This is 5 years ago now. They actually were listening to hams providing call signs and characterizing the signatures in their signals to figure out how the radio waves were traveling through the ionosphere. Why is that? Well, there was the guy that I mentioned earlier, Nathaniel Frisell, got a $1.3 million National Science Foundation grant to go and study this. So what they've been doing is they've been using this satellite to record signals. Golden ears, and the reason that this is important is that when they're recording these signals, they don't know what's going on. They're just seeing that the fact that there are signals taking place, and they've recorded them. And what they're asking hams to do, the golden ears, is to basically play back those signals, identify when the recording was made, that they've got there's a rather long name here that characterizes when and where it was recorded. But in this waterfall, you can see these little red lines. Well, that's CW. So if you're studying propagation and you see a signal in the ionosphere, you don't know where it originated and you don't know where it ended. So what they're doing is they're asking hams to listen to these, characterize the different signals that are heard in there with an originating and a terminating call sign. They know where the propagation was taking place. And now they can, with the scientific instruments that's looking at different kinds of parameters associated with that signal, now they can see what's happening and characterize it in terms of where it's taking place and how it's changing over time. So another activity that that's a little bit more action-oriented for participation. Couple of other again X-ray events or geomagnetic events. You can see, because of the heat maps and where these signals are taking place, of what's changing. A few more examples, and again, think about this more as reference and things that can be studied if you're interested, of course. Here was the example that I was showing or thinking I had earlier. But again, it's interesting when you see where the propagation is taking place over the world. An event happens. The NOAA GOES satellite, that is the geostationary operational environmental satellite operated by NOAA. This is the satellite that's providing most of the weather information that the meteorologists are using on Earth. But it also, because it's in geostationary orbit, it's got a great view of the sun and instruments on board to measure activity. But correlating it now with the effects of propagation, notice that from 1505 to 1520 UTC time, lot of propagation here, good signal paths between North America and Europe at a number of bands. This is back in 2013 during higher times of solar activity, obviously. Activity here into the southern hemisphere as well. Here comes that NOAA, the solar event at a little bit after 1600 UTC. Look at what happened to the propagation. And then about 15 to 30 minutes later, it starts to come back. Well, think about how this might be utilized if you're contesting. Think about how it is if you're, it can be pretty frustrating when you think conditions would be right and you just don't seem to be able to hear anybody. Well, that's what I'm getting into. Why is all this important? The solar weather and the importance of studying it is really a big deal toward electrical power transmission. A coronal mass event or ejection event can quite literally wipe out the electrical grid. If a little bit of technical thing here, the solar wind is actually a electric current. These charged particles are moving, and movement of electrons or other charged particles induce a current. They induce a magnetic field. The magnetic field changes on Earth, and you've got an electrical power grid that is nothing but a gigantic antenna, and that magnetic field will induce currents and voltages that would occur that will blow up substations. And this is a big concern for the electrical power industry. We've talked about HS communications, satellite communications. We're talking about your DirecTV signal, or just the fact that most TV stations are utilizing satellites for moving signals around. So even local ones are utilizing satellite communications. The space operators are really interested in all of this, because what happens is with solar activities, the atmosphere expands and induces drag, and satellites will change their position and their orbit rather significantly. We talked about the GPS and accuracy, and something I know much less about, but there can be significant impacts on climate. So again, references on here. The SWPC, the Space Weather Prediction Center, is an organization that's part of NOAA, just located up the road in Boulder, and are monitoring this all the time. All right, so what can you do? Be a data contributor with your normal activities. It's good to know how your signal's getting out, but it's good for everybody else to know. And whether it's anonymized or not, we're kind of a social organization, and it can only help with the research studies. Consider building a personal space weather station. I'm going to do this when the Tapper product is available. I'm looking forward to that. And then just take advantage of your existing resources to make your ham experience better. It affects HF, VHF, maybe a little bit less so on the repeater, the communications with the local repeaters. But man, there's a lot of other things that are really, really fun activities to do. I'll be, I'll upload or work with whoever is going to upload the presentation, but I have a ton of references here that talk about pretty much everything that's been in there. I would encourage you guys, if interested, to go look at the documentation page on the HamSci website, because there's just a ton of presentations that have been put up there. And more recently, Greg put out some information about, or a link to Contest University 2020, which was just held online about a week ago. And some of the slides that I presented in here are from a presentation that Dr. Frisell presented for that. More references, still more references. Here's that link to the Contest University, where I did get some slides. And, this one, going back to that solar activity that's going on, this is a site that will help you read that. And I'm not going to go over this stuff, but I provided a few more fun pictures and information back here that just kind of supplement a good bit of the information that I provided. Well, that's it. I'd be happy to try to answer any questions if that's possible. I hope I didn't put you to sleep. I find I'm fascinated by this. I know I've had conversations with a few people that that pay attention to this, but I hope you learned something, and be happy to help guide you if you got a few more questions. And I see there's a chat. Yes, it does. Does PSK reporter count as participating? Absolutely. That data becomes public. That data is getting scraped and is part of the analysis that is taking place.
Well, Loren, would you be interested in maybe we could make one of these a club project at some point, like a personal space weather station?
I would think that'd be good fun. It's not available yet. I know that they have finalized at least the modular components, and they're doing board layouts for them now. So I think it'll be a little bit before that's quite ready. But I'll track that.
Good. And without getting too far ahead of ourselves, we're trying to get the gentleman from NOAA, who is an expert in space weather. Loren has been in contact with him. We'd like to get him to present to the club on space weather. He's a wonderful presenter. We just would like to do it in person if we could do it, depending on how long this COVID thing stays with us. We might have to.
Yeah, this guy is a hoot. He is. I think the word to describe him in space weather is passionate and good fun. And it couldn't do it justice if we did it on Zoom. He's very animated, and it would be fun to get him walking around the front of the room to give that presentation. But I hope just gave a sample of some of that. He goes into a lot more detail of why things happen and more specifics about of how these effects actually work. Does antenna orientation matter? That's a good question. The answer is yes, it does matter, because the ionosphere can do things like shift polarities of the signal. So if you have a horizontally oriented antenna, there's nothing to say that signal may not come in vertically polarized or even rotating because of effects in the ionosphere. Think of the ionosphere as a sheet of glass. And if you remember from high school physics class, the refraction that you get, or the reason that your arm looks bigger when you stick it in water is because of light refracting. Well, light and radio signals are essentially the same. They're electromagnetic waves that are traveling, and when they hit a medium, they are bent. They're either absorbed or bent or reflected. And there can be ducting that takes place, and in the course of that ducting, things happen, and so the orientation matters. But I'm not necessarily certain that you can do anything about that. I mean, you got the antenna positioned the way it is. I think it's something you end up having to deal with.
Right. At Contest University, they had a discussion about all this, and one of the possibilities, if you're more serious about this than many of us are, is you can have horizontally polarized and vertically polarized antennas, and you can just switch between them if you're having an issue. And a lot of us don't have that luxury. A lot of us are just hoping we can get up any antenna.
Tough to do that with a big Yagi, but yeah, where you do see it in particular, and not for the same reasons, but in satellite communications, you'll frequently see antennas that are, crossed. So it's a Yagi with two orientations. And one of the reasons you do that is that the satellites are tumbling. And in the course of the transmitting antenna rotating, the signal polarization is going to be changing. So that's why you would use cross-polarized or circular polarized antennas for satellite work.
Okay, any other questions?
Let's see, does the MUF, the maximum usable frequency provided on the KEØHZ web page, vary with location around the world, or is it a single number for the whole world? I think the reason is that they publish it, kind of for a 24-hour period based on the solar activity that they're expecting for that day. So it's going to be different depending on the time of day where you are. But I think that's why they basically say, here's the daytime activity, here's the nighttime changes to that. Locally, absolutely, there can be variations around the world. And I didn't talk about it, but there were a couple of pictures at the end of the presentation that you could go back to and look, after it gets uploaded. But they talk about traveling ionospheric events where, for some reason, there's a mass of ionized particles that are moving through the ionosphere, and they will affect propagation locally, enhance it or degrade it, whichever the case may be. And they're very hard to predict. So part of the activity of collecting more and more data is, can they learn how to characterize them a little bit more accurately and provide more timely types of forecasts? And Jim says, check out Space Weather Woman, WX6SWW. She presents on the, the Wednesday night video cast. She does a section in there, but she's also pretty active on a YouTube channel with a weekly propagation forecast, or a weekly solar forecast. If you're into it, pretty entertaining. Ham Nation, that's correct. So she's a pretty much a regular on that show. Well, I'm talked out. No more questions, but you guys can reach me if something comes up and got any questions. Just a little background. I got involved with the space weather guys earlier this year. The company I'm involved with was participating in an accelerator program called the Space Data Fusion Accelerator that was run at the Catalyst campus in Colorado Springs. And it was sponsored by the Air Force Research Lab out of Albuquerque. And basically it's data associated with space, and in particular satellites. And space weather causes all sorts of problems for satellite operators, from motion, these gigantic the size of school bus antennas that are in geostationary orbit that have gigantic solar panels. The solar wind is traveling at something around the 300 to 400 kilometers per second. The protons, they're not that dense, but they still have some energy and they can move satellites. And not only that, but they can also penetrate shielding and do crazy things to the electronics inside. So having an understanding of when and where these are happening and how intense they are, not just the communications, but the satellite operations that we are so dependent on, are really, really important factors. So that was my reason for getting in contact with the SWPC, the Space Weather Prediction Center, and getting acquainted with some of those people. But I was on a call today with the Air Force Research Lab and some of their space weather experts down in Albuquerque. And just, you know, flying satellites, what's going on with them? We lose them because they move. We try to understand why we lose communication links. We try to understand why we end up with what they call bit flips, because a proton hit a semiconductor inside the satellite and disrupted something or other. So this is a far-reaching problem, and hey, here's an opportunity to contribute to the scientific investigations. So I encourage you people to learn more.
Well, Loren, thank you so much for a real informative talk. And like Loren said, if you have questions, we can shoot them to Loren, and I'm sure he'd be glad to help you out. Is there anything we need to discuss before we adjourn tonight's meeting? I'll take that. Oh, I guess Stu just gave me gave a thumbs up to Loren's talk. That's good. Anybody else have anything? I guess not. Well, let's adjourn then, and we'll plan on the next monthly Zoom meeting in June being via Zoom. I think for the foreseeable future, we're going to be on Zoom.